In this clip, we're going to look at the B2 system. And we're actually going to learn a whole bunch of different things from looking at the B2 system. First, B2 is an example of a homodiatomic molecule. That's to say, the two atoms in the diatomic molecule are the same. They're homo. And it will be a springboard then in the next clip for OF+, which is a heterodiatomic molecule. So it's the first objective of this clip. The second objective of this clip will be to look at first and second order orbital diagrams. The diagram we're going to look at here in this clip will turn out to be the first order orbital diagram. So this first order orbital diagram will be a springboard for OF+, but it will be a springboard also for second order orbital diagrams. And third, we're going to look at the overarching principle, the variational principle. The variational principle derives from Schrödinger and Heisenberg. And it says the following. The lowest energy MOs are the most bonding, lowest energy orbitals possible. The highest energy MO is the most, put in chat what you think it is. The highest energy MO is, put it in chat. Put in chat. The most anti-bonding, highest energy orbital possible. So this is the variational principle, and it is a direct consequence of Heisenberg's and Schrödinger's equations. So we have our three purposes: to set the stage for heteroatomic diatomic systems, which we'll do in the next clip, to set the stage for first and second order orbital diagrams, which we'll do in the clip after that, and to learn the overarching principle controlling mixing, which turns out to be the variational principle that we're always trying to make in the final MOs, the lowest energy and the highest energy MOs possible. Okay, so we're going to do this for B2. We have a lot of goals in mind, and first thing we need to know the energies. Boron 2s is minus 15 EVs. Boron 2p is equal to minus the energies of these orbitals is minus 8.5 EVs. So we're now going to draw the diagram, and as we had the rules here, I'll put on the left. Here are the three boron orbitals, p orbitals. Put in chat the energy of these three p orbitals. They're all at the same energy. What energy are they? I just said minus 8.5 EV. Down here we have it at minus 15 EV. The 2s, that's for the left atom. And notice that those brackets mean that I'm placing, although these pictures look like the orbitals are at a different energy, they're actually at the same energy. I've just drawn them this way to save space. Here they are, at the same energy. Here's this one at the same energy, and so forth. And now we're about to mix the two. And we want let's look at it from the viewpoint of the variational principle. We want to mix the orbital that's lowest energy possible. Anything that we can think of that's lowest energy possible, that's actually going to be an MO. Put in the chat what the reason for that is, what the principle behind that is. The variational principle. And what makes things low in energy? What makes mixing low in energy is strong constructive interference. And what else makes low energy? Put it in chat. Two orbitals that are the same in energy to start off. So, the lowest energy orbital possible, I'll draw it right here, is going to be mixtures of those two lower energy s orbitals. So, we have shown here. And if we add the two to make these two orbitals, I'm going to have to subtract the two. So, it's following just the rules as we always know them, and we can see that we're also obeying the variational principle. We're trying to make the lowest energy orbital possible. How much are we going up and down? Put in chat. How much are we going up or down? In EVs, just put it in chat. I'm going to choose 3 EVs as an average. Is this bottom orbital? Is this bottom orbital psi 1 or psi 2? Put it in chat. Psi 1 or psi 2? It is psi 1. We're adding the 2. So now let's go back to looking at the work here. We've mixed that pair of orbitals. That they're all used up. With the remaining pair of orbitals, what's the lowest energy orbital we can make? It's this one. With constructive interference, if we add the 2, we have to subtract the 2. And a new question. This orbital here, look at it carefully. Is that psi 1 or psi 2? Look very carefully at the left orbital and the right orbital. Is that psi 1 or psi 2? Put it in chat. It is psi 2 in this case. And again, we're going to go up and down 3 EVs. So I go up and down 3 EVs. It's sort of an average bond strength. And there they are. We've used up all the sigma interactions. We just have the pi interactions. Are pi bonds stronger or weaker than sigma bonds? Put it in chat. They are weaker, maybe 2/3 the strength. I'll put them at 2 EVs. I'll draw them right here. Bonding. And pi orbitals always come in pairs, by the way. There's the pair of bonding orbitals. There's the pair of anti-bonding orbitals. And the last thing we can do is draw the lines that indicate the energies of the various orbitals. And what we've drawn here is the first order B2 diagram. And why am I calling it first order? We're mixing these orbitals as well as we can. What goal is it that we're really trying to achieve? Put it in chat. What goal is it that we're trying to achieve? The variational principle. This orbital should be the lowest energy orbital possible. And the question is, for B2, is it? And this is the key. We are going to mix orbitals that are we're going to mix orbitals that are I'm sorry, let me just say that again. This sentence is in the key. Let me read it in orange. Mixing goes to near zero for initial orbitals that are 20 EVs apart. So if the two orbitals are 20 EVs apart, so for example, in fluorine, 2s was at minus 40 EVs, and 2p was at minus 18 EVs. In fluorine, can 2s and 2p mix according to the sentence in red? There are 22 EVs apart. They barely mix. Here's the crux. In boron, the 2s is at minus 15 EVs. The 2p is at minus 8.5 EVs. Put in chat, how many EVs apart are they? Put it in chat. 6.5 EVs. Can boron 2s actually mix with boron 2p? Yes. But could we do that mixing here? No. Because what mixing must always come first? Mixing geometry, molecular geometry equivalent orbitals. So boron 2s is in striking range of boron 2p. We should get some mixing. But we cannot do this in our first order diagram because we must mix geometry equivalent orbitals first. Okay, we'll get back to that boron in the clip after this, but remember we're going to go back to the heteroatomic system, OF+, and I made that clip for the previous lecture, so the previous lecture, it talks a little bit about CO2, but we're going to look at OF+, and the springboard for that is from the B2 diagram.